So good morning, and once again welcome to another session, and we're going to start on transformers. In this topic, you're supposed to know some key things like the principle of operation of the transformer, the EMF equation, the construction of a transformer, and basically the principal operation of three-phase transformer. From there, you're supposed to know the applications and some measurements that we do in transformers in terms of the iron losses and the copper losses, or the open circuit losses, or the short circuit losses. So those are the areas we need to measure on. And the first thing is first to understand the principle of operation of the transformer. The principle of operation of the transformer. So we're going to do this with the aid of a diagram, and I'll draw a diagram here. So this is expected diagram, and this diagram is that it operates on the principle of electromagnetic induction. So first thing, we normally have the primary windings and the secondary windings that are not electrically connected, but they are linked using the core, and the flux is the one that's able to link them. So the flux moves around the core of the transformer, and when it moves around the core of the transformer, then we shall be able to have an EMF induced in the windings. So for us to be able to cause the primary current to flow, we normally connect a primary voltage VP. VP is connected to the primary windings, and because of the resistance of the primary windings, the current IP will flow towards the core of the transformer. And when that one is, when the primary IP flows, then we shall establish what we refer to as magnetomotive force. Magnetomotive force is required to cause the flux to move around the core. And once the magnetomotive force is cause the flux moves around the core, the flux will cut the secondary winding and shall have an induced EMF referred to as the secondary voltage, is Vs. So long as there's no load, they don't have the secondary current. So for us to have the secondary current Is, there must be a condition for connection for the secondary load. Take note of that, because this is a key issue. We normally have a voltage induced in the secondary winding, but this voltage will hang on the terminals provided there's no load on the secondary. So for us to measure the current in the secondary, we must have the load connected in the secondary terminals. But the primary current will be there because of the resistance of the primary windings. And as a result of that, the magnetomotive force produced due to the number of turns and the current flowing will cause the flux to move. So this is the diagram expected to be drawn when explaining the principle of operation of a transformer. So the first key thing is that we normally state is the operation. Yeah? So when the primary winding is connected to a voltage supply, primary current IP flows due to the resistance of the primary winding. This produces magnetomotive force is normally abbreviated as mmf, which is given by Ni, that causes the flux to move around the transformer core. So the statement, when the flux cuts the secondary winding, an EMF is induced. EMF is electromotive force. An EMF is induced in the secondary winding. Vs, using the principle of electromagnetic induction. So the last statement, with the load resistor RL connected across the secondary terminal secondary current IS flows. So this is the principle of operation, and it's very clear that any time you're expected to know the principle, the basic diagram we're going to be using as a standard diagram. So we are saying that with the load resistor connected across the secondary terminals, then we shall have what at first the secondary current from the secondary current from the diagram that you're seeing there. So from here, from this area, we're not supposed to determine the EMF equation of a transformer. And you normally expect that when a flux is moving, it moves in a sinusoidal shape. So we are going to determine the EMF equation using a diagram. So the EMF equation of a transformer of a transformer. Now we're going to use this, we are going to do this using a diagram. So this is 5M. So this diagram is expected for us to use determination of the EMF equation. And you are seeing it, the oscillation or the flux moves only for a single cycle. When the flux moves for the single cycle, it's very easy because at the end of the day, we shall have a repetition of single cycles. So when you look at this diagram, anytime you're going to be analyzing the AC waveform, it's analyzed at a quarter a cycle. And the reason is because at a quarter cycle is when you have the maximum displacement. And we can call from the basic principle is that the EMF normally induced is normally proportional to the magnitude. The EMF is normally proportional to the velocity at which the flux is produced. So when you have this, When you look at the sine wave itself, at a quarter cycle, then you shall have 4 repetitions. That means the average of this is normally at a quarter cycle, because we have 4 sections of quarter cycles that make the complete cycle. And when you look at this, the flux is normally represented in terms of a sine wave. So the flux have a maximum displacement. This is the standard expression for any AC expression. And that is normally given in terms of the maximum displacement, and the other sine of omega t is a phasor angle that is at the point at which the conductor cuts the flux. So when you have this, we normally say that the average flux is produced at a quarter cycle. So the average flux is produced at a quarter cycle. Since the EMF produced is proportional to the rate at which flux is cut, then we shall have the EMF, the average EMF, the average EMF will be given by. So we know that average EMF is supposed to be given by the flux over quarter cycle. This is the flux multiplied by that quarter cycle. This is what we have this as the total flux divided by a quarter cycle. We have this T. So we shall have this a quarter cycle. But T is supposed to be inverse of frequency. So this is supposed to be here. It's just the flux. T is supposed to be inverse of frequency. When I put it there, they should have the average EMF. Supposed to be phi over 1 over 4 F. So this, which gives us phi m sine of omega t over 1 over 4 F. So then it goes above there, we shall have 4 F phi m sine of omega t. We have this expression here. So from there, you're supposed to recall. From the previous knowledge of gathered in the principle of electricity or in electrical principles, you're supposed to recall that the form factor is supposed to be given as RMS over average value, as RMS of average value. So this is what we need to call, and you take note that this form factor must be 1.11. It's a standard value, and you expect to know that form factor is 1.11. So when we're going to express this EMF produced, average EMF produced in terms of the form factor, then what do we have as the equations? Then we shall have 1.11 is supposed to be the RMS value. Our average value is 4 phi m sine of omega t. So for us to get the RMS value is supposed to be 4.44 f phi m sine of omega t. So this is what we expect from the average induced voltage of the AC equation. When you have that, then you must remember that you must remember that the EMF produced is proportional to the number of turns of the windings. So for the primary wind, since the EMF induced is proportional to the number of turns of the winding, the primary voltage Vp will be given by Vp supposed to be 4.44 F phi m Np sine of omega t. And for the secondary, corresponding secondary voltage, Vs shall have Vs as to be 4.44 F phi m N of S sine of omega t. So by dividing the primary and the secondary voltage, we'll have Vp over Vs. And this other end, what shall we be having? We shall be having 4.44 phi m Np sine of omega t. Then this other end, we shall find the Vs as 4.44 phi m Ns sine of omega t. So the common factors will cancel out so that we shall have our Vp by Vs being equals to Np over Ns. So this is an expression that we need to be aware. This is how this expression is arrived at. So we might be having a background knowledge on how to get this, how to use the formula, but this is how the formula is arrived at. So let us proceed. One of the things we need to understand is to know the kind of transformer test we need to have in place. And the reason why we are determining the transformer test is so that we can be able to determine the efficiency of a transformer. So basically there are two types of tests that exist in a transformer. What I refer to as the no-load test. The no-load test is also referred to as the ion test and also the open circuit test. The reason why it's a no-load test is because you want just to determine the heating that's developed across the core of the transformer due to the movement of the flux. As a result of that, we shall be eliminating the secondary winding out of the circuit. And that one will not give us the no-load test. When the secondary winding is included in the circuit in the test, then we talk of the load test. So basically, these are the things we need to be aware of that we need to understand on this. Then for this case, we have to understand why we have this. So because we are going to do the transformer test, first we need to understand the losses. What kind of losses do you expect to be measured in using the transformer test? So basically, there are two types of losses, whatever as the iron losses and also the copper losses. Copper losses is measured when the secondary windings are included in the circuit. And the iron losses is measured when the secondary winding is not included in the circuit. The meaning of not being included is they are open circuits in secondary terminals. So there are two basic types of transformer test. So yeah, there are basically two types. Of transformer test. So the first one is the ion, whatever it was, no load test, and the second one is the copper or load test. So we start with the first one is ion test, whatever as also as open circuit test. So all this we draw them using the configuration of a transformer. So we shall have a transformer So this is the expected diagram, and in this expected diagram, we have to connect the ammeter on the primary or on the input end, and the secondary terminals normally left open. And any time in electrical circuit, when the terminals are open, then we have what we refer to as a high voltage winding. And because at that point the voltage is maximum, but it's hanging on the terminals. But any time the circuit is complete, they normally have a low voltage. Because when we connect the input, a nominal input voltage through the primary end, you have a complete path all the way back to the source. But to the secondary, the terminals are not connected. That's why the secondary terminals is open. So there's no any short circuit that's put there. As a result of that, the voltage appearing here is normally as high voltage, and that appears across the secondary terminals. So it is required that you understand the ion test, the open circuit test, using a diagram. So in this diagram, the ammeter also has got two types of windings. The current coil, which normally in series with the ammeter, and the voltage coil, which is normally shunted with the input, with the ammeter, normally shunted. So at the end of the day, we shall have this kind of diagram. So by looking at it, when you connect the nominal voltage, the meaning of nominal voltage is the rated voltage. The meaning of nominal voltage is the rated voltage. When you connect the nominal voltage across the primary windings, across the input of the transformer, we shall have current will flow due to the windings of the primary. But because the secondary terminals is included, then the losses recorded due to copper shall be very minimum, because the secondary terminals is part of the transformer that's not included. Having eliminated the secondary part, windings as part of the path for the current flow, then we shall have the minimum copper losses recorded by the wattmeter. By comparison of the power losses recorded in the wattmeter to the copper losses recorded, we normally find the copper losses at be very, very minimal, and they are being neglected in the measurement. So at the end of the process, the measurement observed by the wattmeter is normally an assumption that it's a purely the ion losses, since by comparison to the copper losses are very, very minimal. So that's the process that we need to understand in terms of testing. So we need to be able to understand this and put this down in terms of writing. So we are able to understand and to actually refer on what kind of wattmeter is taken. So after doing this, we shall be able to also do the copper test, and we shall be able to observe the difference. We shall be able to observe the difference on what happens. On what happens when we are, and what the difference between the open circuit and the short circuit test. So we need to put down this. When a nominal voltage is applied, when a nominal voltage is applied across the primary terminals, no load current flows, no load. No load current flows through the wattmeter. Since the secondary terminals is open, the losses due to the copper turns, or the copper windings, the losses due to the copper windings shall be minimal compared to the losses due to the no load current, due to the no load current flowing
IO. Therefore, copper losses is negligible, and the recordings on the wattmeter is purely ion losses. It's purely ion losses.
So these losses are also divided into two.
Ion losses are divided into two. Roman 1 is the hysteresis losses, and Roman 2 is the eddy current losses.
So we need to understand the hysteresis losses and the ion losses. So you might be required to know about the hysteresis losses and the ion losses. So just a brief description of what hysteresis losses are. Hysteresis losses hysteresis are due to the movement of flux on the transformer core. And the flux on the transformer core. And therefore this can be minimized by, and therefore this can be minimized by. Therefore this can be minimized by using a silicon, by using a silicon the silicon core material. Silicon core with closely packed plates, So we shall have the eddy current losses are mainly due to magnetomotive force. Magnetomotive force that causes the movement of flux. Therefore, the field assumes the direction of the flux around the core. This can also be minimized by, this can be minimized by using thin laminated cores, thin laminated cores, so that the flux leakages are minimized. So from there we shall be able to do whatever as the copper tests, the load tests, Roman 2, the load tests. Whatever as the short circuit test. So with this one, we shall have the same diagram, but the secondary terminals will be short-circuited. So equally, we use the diagram. Conductor. Oh. So this is the diagram expect use in terms of determining the short circuit test and the load test. And it's a load because the secondary windings are now included in the test. Another thing I'm also observing here is that the windings are reversed in terms of the voltages. So in this case, since the secondary voltage is short circuited, then you have a low voltage. And the primary voltage is open circuit, have a high voltage. The voltmeter will now record the short circuit voltage. That's why it's written as VSH. And the ammeter will now record the current. So what happens at the input at this point, normally have a reduced voltage that is applied. And the voltage is increased until you record a short circuit voltage across the primary terminals. And that time short circuit voltage, the voltage here will be will be maximum value, and here the voltage will now be minimum. And at the end of that, the voltage being minimum, we shall have a more current flowing so that we are able to compensate for the transformation of the transformer ratios. So by having the high voltage and low voltage in this case, on the figure conductor, the maximum current is going to flow. So when you increase the input voltage until you get a short circuit voltage on the primary, on the secondary current, we get a corresponding current because the voltage across the secondary terminals are very, very low. So by so doing, then we shall be having the maximum losses due to the resistance of the copper. And you know that from the basic, from the previous knowledge in terms of the resistance, we normally know that the resistance due to the conductor is a function of the current that is flowing. And since the current will be maximum across the secondary terminals, we shall have the maximum losses due to copper. So the wattmeter will only record the copper losses and the iron loss will be negligible. So in this case,
A reduced voltage applied to the primary is increased until a short circuit voltage is recorded. When this occurs, the corresponding maximum current flows through the short circuit conductor, which in this case is a thick copper conductor. And since the losses recorded due
to the copper windings is determined from the equation I squared R maximum copper losses will be recorded by the wattmeter. In this case, the iron losses are minimal and neglected. So basically we have this, so we expect to have the transformer equation so that we can have an example of a single phase transformer equation in terms of analysis. Then we go to the three-phase transformer construction. So basically efficiency of a transformer. For single phase transformers, for single phase transformers. So we know that TX transformer output supposed to be given by VSIS cos of phi. So transformer output also, transformer output, this can also be given by transformer input minus losses. So the losses we have indicated that can measure are two. Losses, we have the copper losses, is PC, and we have the iron losses, it's PI. The iron losses are normally constant. So when you have transformer input, you shall have the transformer output plus losses. So we shall have this as VSIS cos of phi plus P of C plus P of I. And therefore efficiency is supposed to be VSI of S cos of phi over VSI of S cos of phi plus P of C plus P of I. This is what is multiplied by 100%. So this, we're going to talk in the example so that you can be able to understand how you can use the formulas that have indicated in the previous session, and particularly the one that's proceeding here. So when you look at this question is a single phase transformer of 100 kVA, and it has been given the voltages on the primary and the secondary. The interpretation of these voltages here are that the first one represents the primary voltage and the second one represents the secondary voltage. And in this case, we have been given the iron losses, but there's no copper losses. But effectively, we have been given the resistance of the equivalent resistance at the secondary terminals. So that means basically, for us to determine the efficiency of this transformer, then we must be able to determine the losses due to copper. So one of the things we must understand is how do we get this? Then for us, this is at unity, full load at unity power factor. Then the other part 3 and part 4 is dealing at half full load. Half full load at 0.8 power factor, lagging. So let us start by doing part number 1. So normally for us to get we must first get the secondary windings and the secondary current so that we get the copper losses. So secondary current I of S is given by TX rating. TX means transformer rating over secondary voltage. Transformer rating over secondary voltage. And in this case, we shall have the TX rating is 100 times 10 power 3, because it's a kVA. It's 100 times 10 power 3. And then the secondary voltage is supposed to be given by 400 volts. So we divide this, that is 100 times 10 power 3 Divide by 400 volts. So we shall get 250 amps. This I of S. Then copper losses is supposed to be I squared R, which means that you'll have 250 squared multiplied by the resistance. Equivalent resistance is 0.0144 ohms. You'll have the copper losses. I'll have this as 900 watts. This is P of C. So from there we can now proceed. So TX transformer output. Transformer output at unity power factor is supposed to be TX rating times the power factor. But in this case, the power factor is unity. Then we shall have 100 kVA times 1. Then we shall have 100 kilowatts. So TX input, transformer input, is supposed to be given by TX output plus losses, which is supposed to be 100 kilowatts plus 850 watts plus 900 watts. So you have this as 101 plus 850. 101.750 kilowatts. So now can now determine the transformer efficiency at unity power factor. So transformer efficiency at unity power factor. At unity power factor beginning by TX output over TX input times 100%. So we shall have output is 100, our input is 101.75 times 100%. This around 98.2%. This is the first part of the question, the full load, when delivering full load at unity power factor. So when delivering half full load at unity power factor. So we're going to part 2 of the equation. This is when delivering at half full load at unity power factor. TX output at half load. TX output at half full load. Supposed to be TX output at full load times a half, which means we shall be having 100 kilowatts times a half, which will give us 50 kilowatts. So we proceed from there. Then copper losses at half full load. Copper losses at half full load. Unity power factor is given by a half squared multiplied by the copper losses at full load. We have the number being a half is because we normally with the copper losses we have the copper losses as a function of I squared. As a result of that, the factor determining will be the unity power, the power factor that we are using, and actually when operating at a half load or full load. So since we are operating at a half full load, we shall have a half squared, then PC, and this will be this is a quarter, and the PC we had 900 that. So we have that. We'll have this as 225 watts. So since iron losses are constant, remain constant, we shall have the P of iron losses as also 850 watts. So the TX input, transformer input, is supposed to be TX output plus losses, and this means that we shall have 50 kilowatts plus 850, which is iron losses, plus 225 watts. These are watts, these are watts. So we shall have that's is at 50 plus 225. So we shall have this as 51.075. So TX transformer efficiency shall have this as 50 or 51.075 times 100%. This is 97.89%. So when you look at the two results, the equation that arises from these two results, at this point, at the second part of it, you are operating the transformer at a half full load. But the first part, you are operating the transformer at full load. And we look at the percentage of the efficiency, it's nearly the same. The main key reason why the percentage of efficiency is nearly the same is because you need to understand that when you're operating at half full load, what is changing is the variability of current. So current is going to increase at half full load, but the efficiency of the transformer will remain the same. Since iron losses are constant, we normally have reasons why we shall have the efficiency remaining at nearly the same point. The slight difference between 97.8 and 98.2, yet you're operating at half the rate. This is because at half the rate, the iron losses are constant. So any other factor determining the losses will be as a result of the current flowing. So that will be something that you need to know about. So what let us do on part number 3 so that you understand the scenario when happens when you're given as the transformer having a lagging power factor. So part 3 of this equation, the full load at 0.8 power factor lagging, full load at 0.8 power factor lagging. So at 0.8 power factor lagging means that the TX output, the transformer output, will be TX rating times the power factor, and this is supposed to be 100 kVA times 0.8, which gives us 80 kilowatts. That will give us 80 kilowatts. So the iron losses remain constant. We shall have 50 watts. The copper losses will also remain constant as 900 watts. So when you have this, the TX input will be 80 kilowatts plus 850 watts plus 900 plus 900 watts becomes 81.75 kilowatts. So the efficiency is supposed to be TX output over TX input times 100%, which implies that you'll have 80 over 81.75 times 100%. This means shall have this 97.85%. So similarly, with half full load, which remains as part 4 of the equation, at half full load, 0.8 power factor lagging, we shall have TX output will be a half times TX output at full load is 80 kilowatts. We shall have this as 40 kilowatts. Since we had determined the copper losses at half full load, we still have copper losses. Copper losses PC. Copper losses PC is supposed to give us a half squared PC at full load, which is also supposed to give us 225 watts. Iron losses are constant. We still maintain iron losses. Iron losses as P of I, which will work out as 850 watts. So you can have total losses also, which is supposed to be 850 watts plus 225 watts, which is supposed to be 1075 watts. Now calculate the efficiency. Efficiency is supposed to be TX output over TX input times 100%. In that case, we shall have the TX output as 40 kilowatts, while the input is 40 plus 40 kilowatts plus 1.075 kilowatts. This comes 40 over 41.075 times 100%. So we shall have 97.3%. So basically this is how we approach the equation, and you take note of the power factor, whether it is a half full load or a quarter full load. So we can now conclude that therefore since copper losses are as a result of I squared. I squared referring to the current, a result of current. Then at full load, unity, at full load unity power factor, you'll have copper losses as PC. Number 2, at half full load unity power factor, you shall have this as half squared PC. Number 3, at 3/4 full load unity power factor, we shall have that as 3/4 squared PC. So this is at full load unity power factor, at half full load unity power factor, at 3/4 full load unity power factor. We shall have this as the way it is. So that anytime you're working at a different load power factor other than unity power factor, you take note of that when determining the copper losses.